All right, Giants, welcome back to Pre-Calc, and today we are going to talk about imaginary numbers. Now, we've alluded to these several times. Many of you were exposed to them last year in Algebra 2. However, if you haven't watched the video I linked right above this, please pause this, go back, watch that video on imaginary numbers. It's about 5 minutes, gives a little history, also does a great job, shows kind of that graph with the other dimension that shows kind of the imaginary dimension on our coordinate plane. And that's something that I can't really draw for you, but the video does a great job. Hopefully it can help you understand it a little better. So when we have a negative number that we're trying to take the square root of, so far this year we've alluded to it, but we've said we can't do it. Okay, but in reality we can find it. It's not a real answer, a real number. It's an imaginary number. So the square root of 2i gives us, the square root of negative 4 gives us 2i. Likewise, the square root of negative 25, it's going to be 5i. Finally, this one is pretty important. The square root of negative 1 gives us I. Okay, and that one we are going to allude to at a couple other times here. Now, these also are known as our imaginary numbers, but sometimes they are known as our complex numbers. And complex numbers occur when there's a real number and an imaginary number that are together. So something like 2 plus 5i. Do you see how there's a real number, the 2, and it's added with the 5i? Okay. Another one, and these, I can make up literally anything, just a number at the front. It could be positive or negative. The imaginary number could be positive or negative. Whatever we want, okay? Now, when we are multiplying imaginary numbers, we need to be careful. If we have i's for both of them, I times I is I squared. And so like on this one, we know that 2 times 2 gives us 4. I times I is I squared, 4i squared. But we're not done there because I squared actually equals negative 1. Now some of you might be saying, what? That doesn't make sense. But let me show you why. So because we know that if we're saying I squared, that's the same thing we said up here in the box here, right there. I is the same as the square root of negative 1. So I squared is the same as the square root of negative 1 squared, which when we square it, the square root and the square cancel out, and we're left with I squared equals negative 1. So if we look here on example 1, 4 times I squared is actually going to give us negative 4 as our answer. Okay, now on this next one, 5 times negative 5 gives us negative 25 I squared. I squared is negative 1, so we'll get 25 as our answer there. And our final one on this row, negative I times I gives us negative I squared. Okay, and now we know negative times negative 1 will give us positive 1 as our answer. Now, sometimes we have to multiply complex numbers. So when we're doing this, we follow the same rules of FOIL. Okay, so we do first, we get negative 6. Then outside, we're going to get plus 4i. Inside, minus 15i. And then last, you got to be careful on that one, 10i squared. Okay, now we know that 10i squared is the same as negative 10. So negative 6 and negative 10 combine to negative 16. 4i minus 15i will give us negative 11i. So go ahead if you want, pause it and try this next one. We know once again 4 times 4 gives us 16. Outside would give us negative 12i. Inside would give us 12i. And last is negative 9i squared, which is the same then as negative 1 times negative 9, which gives us a 9. 16 plus 9 gives us 25. And you might notice the negative 12i and the 12i here. Those ones are going to cross out, cancel out. Now, one thing here you might notice, anytime we have the real number is the same and the imaginary number is opposites of each other, those are what we call conjugates, and they cause some things to cancel out nicely for us. Okay, so right here, what is a conjugate? It's when we change the sign of the imaginary number, but we keep the sign of the real number. And that is how they always come. If we have zeros that are imaginary and complex, they will come in pairs. So for example, if 4i is a 0, then we know, now once again, it's not a real 0, but it's a 0, we know that it will also have a 0 at negative 4i. Okay, likewise, if 7 plus 3i is a 0, then we said the real number stays the same, so it's still just 7. Instead of plus 3i, it's going to be minus 3i. Okay, if negative I is a 0, then also I is a 0. And finally, if negative 1 minus 2i is a 0, then negative 1 plus 2i is also a 0. So that can be very useful as it allows things to cancel out nicely for us and kind of eliminate some i's. And we'll continue to look at that on the back. So last week we had to write a polynomial function, except when we wrote our polynomial functions, they always had, they were always nice in that it was just real roots. Okay. Here we have a 0 of negative 3. We also have one of 2i. However, if we have 2i, we know that our third one, since it's degree 3, we need our third one. And we know that third one would be the conjugate of 2i, which is negative 2i. So those are our 3 zeros. Now, we know our final answer. We can write something like this: f of x equals, and we know the first one's easy. It's going to be x plus 3. However, to get the second part, okay, how do I write a polynomial with imaginary zeros? Okay, now I'm going to show you guys a shortcut, and then I'm going to explain how we get that. We need to have x squared minus the sum of the two numbers times x, okay, and then plus the product of those two imaginary numbers. So what I mean by that is, first let's go ahead and find the sum. So our sum is going to be 2i plus that negative 2i, which hopefully you know will equal 0. So sum 0. Okay, now the product, if we multiply those, we're going to get 2i times negative 2i, and that would equal negative 4i squared. I squared is the same as negative 1, so that actually equals positive 4. Okay, so now if we plug this in, we're going to put our parenthesis. We know we have that x squared at the front. Then right here, minus the sum. Their sum was 0, so 0 times x is just 0. So if you want, you can put minus 0. We don't need to. Instead, let's just add the product, which in our case was 4. And that x squared plus 4, remember last week when we had this, we said we couldn't get a real root. If we would set that equal to 0, we'd subtract the 4 over, we'd take the square root, and we get plus and minus 2i, which is what we had here. So good. Now I'm going to show you guys, I worked out, the reason it simplifies this, if we look here, I could have wrote it as x minus 2i and x plus 2i, and I'd FOIL this, x squared plus 2ix minus 2ix minus 4i squared. We'd get negative 1. Those would cancel out, and x squared plus 4 is what we get, which is what we had. The reason I want us to use the shortcut, it starts to get a little bit more complicated. On this one, it wasn't too bad. However, as I'll show you on example 8 in a minute, it starts to get a little bit more complicated as we have complex numbers. So I recommend you pause the video, try example 7. So once again, this time it's degree 4. Okay, and we know it has zeros at negative 3, 5, negative 3i. We also know there's a fourth 0 at 3i. So when we write our answer, f of x we know will equal x plus 3, x minus 5. Okay, then once again, over here what I'm going to write in red, or let me show you, if we wanted to, we could do x plus 3i here and x minus 3i and then FOIL it all. Our end answer would be x squared plus 9. That's kind of a little bit more work, or maybe on this one you think that's easy, and if so, then go ahead and do this. That would be all you'd have to do. You'd have x squared plus 9 you'd put beside it. However, our method up here, we know it's going to be x squared. So we need to find the sum. So if we add negative 3i plus 3i, which you might notice if those two don't have any real numbers as part, if they're not complex, it's just the imaginary, those will always cancel out. So that equals 0. So we don't need to worry about this part. Now the product we do need to worry about. So once again, our product, we need to multiply that 3i times negative 3i. And let me scroll there. So that'll be negative 9i squared, which results in 9. So x squared plus 9 is what we will get there, which, as you see when we did it the other way, that's also what we got. So once again, I don't care if you want to use this way instead, you can. However, on example 8, you'll see why it starts to get very complicated as to what's happening. But you can still do that. So now, example 8 is a complex number for us. So, for example 8, we know, once again, it's going to have a 0 at 1. It's degree 3. Here's the second 0. It's got to be the conjugate of that. So the 2 stays the same. It'd be minus 5i was what it was, so it'll become plus 5i. That's our second imaginary 0, our complex 0. So we know it's still going to start off f of x equals, and this 1 at the front, that one's easy, x minus 1. Now this one's going to take a little bit more work, so I'm going to put it over here to find our sum. It will not all cancel out this time. Okay, so the sum is 2 minus 5i plus 2 plus 5i. We can just add i's with i's. Those will cancel. But 2 plus 2 gives us 4. So our sum is 4. And over here, we also need to find our product. So the product of, I'm going to put them in parentheses, 2 minus 5i times 2 plus 5i. Then we FOIL. 2 times 2 gives us 4. We're going to have plus 10i in the middle, minus 10i, then minus 25i squared. Now, the nice thing about this is the 10i and the negative 10i, this should always happen if you have a conjugate correctly. Those will cancel, okay, and we're left with 4. Now, negative 25 times i squared, which is negative 1, gives us, so that's the same as 25. 4 plus 25 results in a product of 29. Okay, now we need to write it using our formula from up here. So always have this formula handy. We know it's going to be x squared minus whatever the sum was, which in our case was 4, times x. Okay, and then the product we got to add on at the end, which in our case was plus 29. Okay, so another way you could have done that, as you can see, we could have plugged in x minus 2 plus f or plus 5i and x minus 2 minus 5i. Those two would have worked. However, if we do that, we can't FOIL, we have to multiply each term with each term. Okay, and it gets pretty complicated. We have some ix's here. Everything does cancel out nicely, but as you can see, in the end, it's x squared minus 4x plus 29. It's exactly the same. Once again, if you have more questions about this or want to see me do more of these, I can. I just think it will be more work for you, and it's probably easier just to use this formula up here, the x squared minus sum x plus the product. So one more I want to do here. Go ahead and first thing, we know once again it's degree 3. We have a negative 2. We also have 3 plus 2i, which means our conjugate of that is 3 minus 2i. So now, the easy part, f of x will equal, we have right here the negative 2, so it'll be x plus 2. And then we know we're going to find something else using our sum and our product to find what else will go there. So once again, start off with your sum. And maybe I'll put example 9 below that line. But our sum, we're going to add 3 plus 2i with 3 minus 2i. If we add straight down, we get 6. Okay. The 2i and the negative 2i cancel. Now the product, we're going to take 3 plus 2i times 3 minus 2i. 3 times 3 is 9. We're going to have 9 minus 6i plus 6i. Once again, they'll cancel, which is what they should do. And then the final one is minus 4i squared. So that will give us 9 plus 4 because negative 4 times I squared, which is negative 1. And that results in 13. And then once again, from here, let's think back. It's x squared up here minus the sum of x. So x squared minus 6x and plus the product, which in our case is plus 13. And we are done. So a little bit complicated, I know, but please keep working hard for me. Let me know if you have any questions. Make sure to work on the It's Learning assignment for today and take a look at the quiz for tomorrow, please. Make sure we stay on top of things. Let's finish strong.